Good morning, Astronomy 1020, and welcome back to our class. Today is Tuesday, September 8th. We have another 1.5 hour lecture followed by our second lab using celestial spheres. So I hope you're ready for that. If you haven't, you might want to take a moment to print out the handout on celestial spheres so that when we go into lab mode around 1 p.m., you'll be kind of ready to go. Remember, everyone, if you don't have a printer, then it's up to you to take a ruler and a piece of pencil or a pencil and draw out the graph appropriately. Should look something like this, right? So try to do a nice, neat, workman-like job. Okay, so let's get right into it. The goal today is to teach you guys about celestial coordinates and how things move across the nighttime sky. And to do that, we're going to need to think about those angles that we learned about in our last class. Do you guys remember talking about angles and the different types of units we use for angles? Oh, Donovan, I'm loving this. Is that a parakeet?
It's a cockatoo.
Oh, it's a cockatoo? Cool.
Yeah, I'm watching him since my family's gone.
He seems to be well trained there if you just perches on your... Is that... Well, okay, I'm going to leave it there. Anyways, love it, Donovan. Good. Plus 10 style points. Okay, so listen, guys. When we talk about angles, what are the units that we use? I need to make sure you know some stuff before I go forward here.
Degrees, arc minutes, and arc seconds.
Thank you, Christopher. Degrees, arc minutes, and arc seconds. In our last lecture, I taught you guys that everything you see in your field of view is an angle. And because you've learned about the small angle formula, you know that when objects are close to you, their angular size appears large. And as those objects get further and further away, their angular size becomes small. And we can measure them with different units, arc minutes, arc seconds, and for the largest angular size objects, degrees. Let's start today by showing you guys a picture that a friend of mine named Bob Horton took of the local sky. Forgive me if I showed this to you beforehand. Actually, just a moment. I got to get rid of that chime when people come and go. Okay. Let me start off with a picture or two, because I always like to do that. And I want to show you a picture somewhere, maybe slide 41. Let's see if we can do this. Function F, oops, that's F6. Function F5, 41. I don't know if I showed this to you last time, probably not. This is a picture that shows a conjunction between the planets Jupiter, Venus, and the brightest star in the sky, Sirius. And it's seen from what looks like Prospect Park here on the east side of Providence, overlooking the city. Now, in this picture, this big dot is Venus, or I should rather say this bright dot. This dot here is Jupiter. And this dot that you see here is the star Sirius, which, believe it or not, is the brightest star in the sky. Hey, whoever just joined, you might want to mute yourself. That would be a good idea, because I can hear your plates and pans rattling around. Don't make me find you and mute you.
I'm sorry.
That's okay. Is it Austin? Was that you?
It's Professor. It has been me like 6 times.
Oh, geez, Austin. Way to start the day off. Okay, all right. Anyways, believe it or not, Sirius is the brightest star in the sky, and I'm sure it doesn't look very bright in this image here. And that's because this image was taken for aesthetic purposes, and the exposure rate on the camera is designed to capture all the beautiful buildings in the skyline of the city. I assure you that were you standing on Prospect Park, this would look like a relatively bright star to your eye. It's just that if you compare it to the light from the buildings, it's much dimmer. I want you to notice that the light from Jupiter and the light from Venus is much brighter than the light that you see from Sirius. There's a couple of different reasons for this. One is they actually are truly brighter, and another issue has to do with their angular sizes. the angles that these two planets subtend on your sky is much bigger than the light that you get from Sirius. And for this reason, we have a saying that helps astronomers, amateur astronomers, distinguish planets from stars. The old rule goes like this: stars twinkle, but planets do not. And if you're ever looking at an object in your sky, for instance, there are several planets in our sky right now, you can tell you're looking at a planet because it won't twinkle the way other stars do. Another issue that I feel obliged to teach you from optics, this is just a little warm-up to the class today, is that in optics, we distinguish between two types of features that we can see. There are resolved objects. And in your field of view or in your vision, a resolved object is an object that you can see as a disk. For instance, the moon is a resolved object because you can see the disk of the moon, you can see features on it, and your eye can distinguish the difference between the top of the moon and the bottom of the moon. All right, you can see features on it. There are other ways of looking at things or other types of objects called unresolved objects. An unresolved object is one where you can detect light from the source, but you can't make out any features. And in that case, the light that you get is just going to look like a mathematical point, a point of zero dimensions. Maybe in the case of stars with a little bit of twinkling on it. Astronomers refer to this as a point source. Many of the objects that you see on your sky when you look up at night are unresolved point sources. You just see a single twinkling little dot. Some objects, like the sun and the moon, are resolved objects, and you can actually see the disk. Let's go back to that slide for a second there. In this case, Sirius, Jupiter, and Venus are all unresolved objects. We detect a dot of light, but we cannot make out any internal structure. Now check out these moves. In the next picture, he's going to take a small telescope and attach his camera to it. And when he zooms in on the two objects, boom. Now, with a telescope with the power of magnification, he's resolved Jupiter as a small disk. And can you guys see these little dots nearby here? Those are the Galilean moons, discovered by Galileo. Io, Europa, Ganymede, and Callisto. Jupiter is now seen as a disk, and down here, notice that Venus can be seen in a gibbous phase. An interesting thing about the planet Venus is that it actually goes through a set of phases just like the moon does, but you need a telescope to see them. Class, is Venus a resolved object in this picture? Yes or no? Tell me.
Yes.
Yes. Most of you are saying yes, and that's correct. Venus is a resolved object. And you know that because you can actually see the curvature of the shadow on the gibbous phase. If it was unresolved, you wouldn't be able to make out any interesting features at all. How about the Galilean moons? Are they resolved or unresolved objects?
Unresolved.
Good. How about Jupiter here?
Resolved. Resolved.
Yeah. You can see that it's a disk, and if you have a small telescope, you can sometimes even see cloud stripes on it, the bands of ammonia clouds on the planet. It's pretty cool. Okay, good. So it seems like you guys understand what I'm talking about. That makes me very happy. Obviously, if you're going to measure the angular sizes of things like planets and their moons, angles like degrees are much too clumsy a unit to use. Because remember what we learned last time. The angular size of the moon is roughly 0.5 degrees. That's its angular size. And the angular size of the sun, by a curious coincidence, is also 0.5 degrees. And that's something of a coincidence. The sun and the moon are the largest, in terms of angle, they are the largest angular objects you can look at in the sky. Everything else is going to be smaller than half a degree. You know, it's a weird coincidence that the moon and sun happen to have the same angular size. For this reason, when they align in the sky, we can get the beautiful total solar eclipse, which I'll show you a picture of here. During a total solar eclipse, the angular size of the moon perfectly blocks the angular size of the sun. And when you block the disk of the sun, you can suddenly see some eerie white light surrounding the sun. This is from an outer wispy layer of the sun's atmosphere known as the corona. And we're going to learn about the corona when we get to our lecture on the sun. The corona is not part of the disk of the sun. It's an outer wispy atmospheric layer. And while it does give off light, when the sun is up in the sky, the light that you get from the disk is so much brighter than the light from the corona that the corona gets washed out. Once the disk of the moon covers the disk of the sun, it's dark enough where you can actually see that creepy light from the corona. And apparently it's quite beautiful to look at. If you think about it, the sun is nowhere near the same size as the moon, right? The sun is much bigger than the moon. But the sun is also farther away. And if we think about what we learned in the small angle formula, it must be that the ratio of the sun's diameter to the moon's diameter is exactly the same as the ratio of the distance to the sun versus the distance to the moon from Earth. And that means it's something of a coinkydink that both of these objects happen to have an angular size of half a degree. Had the sun formed as a slightly larger star, had Earth been a little closer or farther to the sun from its orbit, had the moon formed larger or formed closer, none of this would be true. And we would not be able to see these totally amazing total solar eclipses. So that is something of a weird coincidence. Furthermore, it's not always true that the angular size of the sun and moon perfectly line up. From time to time, you can get a rare type of an eclipse known as an annular eclipse. And during an annular solar eclipse, an eclipse happens when the moon is a little bit farther away from Earth than normal. And this tends to shrink the angular size of the moon so that it does not perfectly cover the disk of the sun. And then you get this annulus, or this ring of fire from the sun's photosphere. And this is a beautiful and rare type of eclipse to witness. So if you're following me, the angular size of the sun and moon did not have to be so close to each other. It's something of a magical coincidence. On the other hand, we're going to need smaller angles because we're going to want to look at things like planets. We're going to want to look at things like tiny stars. And as this slide will show you here, the typical angular size of a planet, like the disk of Jupiter, is very, very close to 1 arc minute. So I wanted to review this because I introduced this stuff really quick at the end of class, and I don't think you had enough touchy-feely time with it. So I want to really drive the point home. An arc minute is what happens if you break a degree up into 60 more wedges. An arc minute is kind of like looking at a soccer ball from half a mile away. Class, do you think you'd be able to make out the pentagon checkered black and white pattern of a soccer ball from half a mile away? What do you think? Chris says no. Devlin says no. All right, most people are saying no, and that's correct. But oh, okay, Arunsak, anytime, come back. Your eye, the human eye, can see down to a limiting resolution of about 3 to 4 minutes of arc. Anything smaller than that will just be a speck of goo in your vision. Doesn't matter where it is. If it's on it could be a little paramecium in your eyeball. It could be a quasar at the edge of the observable universe. If it's bigger than 3 minutes of arc, you can see it. Smaller than 3 minutes of arc, you can't. By the way, Jupiter roughly subtends 1 minute of arc. So arc minutes are good for the angular sizes of planets. However, for stars, we need much smaller angles. That's where we make up the arc second. We break 1 arc minute into 60 more pizza slices. And then an arc second is kind of like looking at a dime from 2.5 miles away. There's no way in hell you could make out any features on a dime from 2.5 miles away. Betelgeuse, one of the largest stars in our neighborhood, both in physical size and in angular size, has an angular size of 0.055 arc seconds, or 55 milli-arc seconds. The angular sizes of stars are truly microscopic. And for that reason, they are literally nothing more than little mathematical points of light on the sky. Okay. Now that you know about angles, it's time for us to use those angles and talk about the motions of stars and planets across our sky. And to do that, we're going to develop this concept that we borrowed from Greek astronomy. The Greeks believed that stars were literally stuck to a crystalline sphere which rotates around Earth. Now, that's not true. Stars lie at a variety of distances from Earth, but in some sense, it's not helpful to start thinking about all of that stuff right off the bat. As Earth spins daily on its axis, we see stars rise and set, and for all intents and purposes, from an observer's point of view, stars do seem to be rotating around the planet on some type of fixed sphere, the sphere of the sky. And that's actually a useful concept, a useful place for us to start when we start learning about the motions of stars. So let's go to a crappy little slide here. Here's a picture of the celestial sphere, and we're going to take some notes identifying 3 points on the celestial sphere: the north celestial pole, the celestial equator, and the south celestial pole are reference points on the celestial sphere, and they are also reference points on your sky. Why don't you follow along with me as we take some notes? Introducing the celestial sphere. The celestial sphere is a useful lie. It could also be thought of as a sphere of infinite radius centered on Earth, on which stars, planets, suns, moons, galaxies, anything you could imagine seem to rotate. There are some key points on the celestial sphere. The key points are the north celestial pole, which is the projection of the North Pole onto the sky. There is the celestial equator, projection of the equator onto the sky. Dot, 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 okay. Projection of the equator. Sorry, my handwriting's kind of bad today. And then the south celestial pole. Which you can imagine is the projection of the south pole onto the sky. Let me give you a moment to catch up while I sip this delicious drug called coffee. Okay. I'm going to try to write neater for the rest of the day. That's my goal. Donovan, let me know when you're done writing. You're good. Okay. I need to erase. Speak now. Oh, Devlin says 1. Okay, all right.
Can you
I need
just
some more time too.
Yep, that's fine.
Can you erase the top two, just the stars? Or asterisk, whatever you want.
Yeah, I'll just wait until you guys are done.
Okay.
Or, you know what? That's a good idea. I guess I should be normal. I could do that. I could be normal. Before we leave this topic, I have one more very important star to share with you.
Quick
This-
question.
Yeah, hit me.
The south celestial pole, it's the same thing as the north celestial pole. It's just a projection of the south pole on the sky.
Correct.
I am all set.
All right. Everyone else all set?
I'm writing down the last one.
All right, I'll start up here then. This is one last bullet point or star, one more concept that I want you guys to drive home, okay? And this one is not as obvious as the rest of it. You can always see exactly 1/2 of the celestial sphere in your, wait for the big buzzword here, okay, in your local sky. Underline local sky because that's an important concept that we have yet to develop. You can always see 1/2 of the celestial sphere in your local sky. Most of you probably don't even know what the hell I mean by that. And so I'm going to explain it with the help of a graphic. Take a moment here to look at this picture and think about what it means. When you're standing on Earth, and let's say for argument's sake that you're standing where this yellow arrow is, right here, okay? You tend to think of yourself as a little dude standing on a big Earth, and your little dude self is somehow surrounded by this little dude sky that you see right here. But in fact, what you think is your little dude sky is actually a big dude sky. And the sky that you see, if you ignore buildings and trees, if you're in a flat desert or a very flat field or on a boat in the ocean, the sky that you could see would be a hemisphere, 1/2 of a sphere, and it would cut right through the center of Earth. And you would be able to see stars that were located here and here. The reason why that's not obvious from a picture like this is this picture tells a little lie. It makes the Earth look somehow big in comparison to the celestial sphere. So it makes it look like you won't be able to see around the curvature of Earth. In fact, by definition, the celestial sphere is a sphere of infinite radius. And for that reason, the Earth is very small in comparison to it. So if I were to draw that picture cruder but better, I would show the celestial sphere as a big circle, and in comparison, the diameter of Earth is just a microscopic little dot. So that if you are an observer and your head points in this direction, there's sort of no difference between the line that goes from your feet to the sky versus the line that goes from the center of Earth to the sky. So your horizon would stretch out in this direction, and you'd be able to see stars that were all here on this part of your sky. This is what we're going to define in a moment as your local sky. But honestly, if I were learning this for the first time, I think I would like someone to tell me that explicitly. You can always see in a flat local sky, you can always see exactly 1/2 of the celestial sphere. Why is that important? It's important because it teaches us that stars tend to rise and set, and most of them will be up for close to 12 hours during the course of a day. Stars will spend 12 hours above your horizon and 12 hours below your horizon. Now, that's a little different depending on where if they're close to the North Pole or South Pole, it could be a little different, but that's a good starting point in any case. Okay, so you can always see 1/2 of the celestial sphere in your local sky. Good point to remember. Now that I've defined the celestial sphere somewhat crudely, it's time for me to mute my phone. And it's also time for us to look at a slide depicting what's called your local sky. And this is a picture that I provided for you in the lecture handouts for lecture number 2. But we're going to actually have a little Bob Ross moment here where we attempt to draw this. This picture is a picture of the hemisphere that makes up your local sky. And we need to identify some key points on it so that we can describe the motions of stars through our sky. Basically, you guys need a little vocabulary lesson, okay? And you need a little drawing class as well. So let's erase. And let's try to make a 3-dimensional picture of the local sky. For this portion of our lecture, it'd be helpful if you guys had a ruler and or a protractor. Oh, cool. Show us your ruler. We are the world. Okay, I love this. You got your rulers. This is going to help you. If not, get crafty and use the flat edge of your calculator, all right? Now, if you're going to draw this local sky in a typical notebook paper, I'd recommend maybe a 12-centimeter line. I have to make a slightly bigger one because I'm on this board here. I'm going to leave yourself a lot of headroom. Title this a 3D view of the local sky, okay? A 3D view of the local sky. Am I having focus issues? I need to call up that Logitech. Sorry, I need to get the Logitech app going here. Okay, a 3D view of the local sky. Let's start off by drawing a line. I'm doing mine 60 centimeters. You might want to do yours as 12. And I'm going to put a dot right at the midpoint. So if you made a 12-centimeter line, putting a dot at 6 centimeters is ideal. And what we're going to attempt to do is we're going to attempt to sort of make a dome, okay? So I'm going to, since my line was 60 centimeters, I'm going to use the radius, or half of that, and I'm going to make a dot that's 30 centimeters up here. This is just a little trick to help me make a good dome. That's where the top of my dome should be. In fact, here's some other tricks. I can actually find a few more dots along the dome by marking out the radius. This is just to try to do a nice workmanlike job. This way I can kind of connect the dots in my dome. Now my dome is going to look domey, okay? So I'm going to draw a curve through those dots. Oh yeah, baby. And look, I've made a passable dome. Okay, now what I want you to do is I want you to take your pencil and make a little dash just above the dot and a little dash just below the dot. And what we're going to do is we're going to draw a line connecting the edge to those dashes to kind of make a little oval. This oval is going to be the ground, the field that you are standing in as an astronomical observer. In fact, if you want to get wicked artsy, you can take a green marker and you could put some grass in there, or maybe some desert sand or some blue waters, whatever you'd like to do. You just want to find yourself in a flat field somewhere. And look, we have a passable representation of our 3-dimensional local sky. First thing we do when we draw our local sky is we choose our directions. This is very important. I am a right-handed person, so I tend to always put north on the right-hand side. You guys should follow my lead here. I put north on the right-hand side. That makes south on the left-hand side. In that case, east will be towards the plane of the board, and west will be into the plane of the board. It's important that you kind of establish for yourself where north, south, east, and west are going to be, because the motions of the stars will depend upon that. Warning to the class, your book, The Cosmic Perspective, they always put north on the left-hand side, probably because they hired some sinister left-handed artist to draw the picture, okay? That's what they, you know, they have a high percentage of left-handed people at the Rhode Island School of Design. So I think they hire these sinister left-handed artists. Now, you can put north on the left-hand side if you're a sinister left-handed person, but I don't like doing that because, well, I guess for no good reason. Other than a lot of my good diagrams that I managed to get from the internet, the really good diagrams also have north on the side. So I think we should all stick to that for now. But be wary that the images in the book are a little bit different. Okay, we're now going to identify what are called the 5 fundamental positions of your local sky. First thing I'd like you to do is make a dot right up here at the top of this dome and put a little Z above it. This is, oh, by the way, if you want, you can put an observer in the center of the field. Just put a little dude there to remind yourself that's where the observer is. Okay, the little dot at the top is the zenith. This is your first vocabulary term. It's simply the point overhead in your local sky, okay? So it's the point directly above your head. Next, we could indicate this oval here. The oval that we drew in is called the horizon, sometimes the horizon ring. So let's draw an arrow up to the horizon. The horizon is a 360-degree ring at the base of your local sky. Next, we're going to refer to this arc that runs north to south as our meridian, okay? The meridian is an arc that rises due north, reaches your zenith, and sets due south. You can label up here, this is your meridian. Actually, you know what? No, don't do that. Let's leave that clean for our diagram. Okay, there's 2 more positions we need to indicate. But I'm going to give you guys a moment to catch up to me there because I might have been faster than you. The more people that share their video, the better I'll be able to pace this, okay? So when I can see that you're done writing, that's when then I know to, like, you know, how to pace myself appropriately. Emily, let me know when you're done writing. Kate, let me know when you're done writing. Oh, she's good. Emily, you good? Okay, cool. All right. If I have a local sky, let's say I'm located in Rhode Island, which is a safe assumption for most of us. Let me go back a slide here. If I'm located in Rhode Island, I'm roughly halfway up the globe. Should I be able to see the North Celestial Pole in my local sky? Austin, Kate says yes.
Yes.
Elijah says yes. Okay. Caroline, yeah. So I should because I can see half of the celestial sphere, and this point is most likely going to be on my local sky if I'm anywhere north of the equator, okay? Let's go ahead and draw in our North Celestial Pole. I'm going to use a blue marker for this. And it's going to go from the foot of my observer up to somewhere in the northern part of the sky. So we'll draw an arrow. This is the north celestial pole. A famous object resides at the north celestial pole in your sky. Do you know what it is?
North Star.
Right. What's the name of the North Star, Austin?
Don't know. I call it the North Star.
Okay.
Polaris.
Oh, who knew that? Oh, Arunsak knew that.
Yeah.
Somebody else did too. Cool. Yeah, so a couple of you have heard of Polaris before. Let's put a star on the sky. I want to show you guys a couple of funsy pictures. Label that as Polaris. Let's just pretend for a moment that this is the class you thought it was going to be, where you learned all kinds of cute things about constellations, and you will learn some cute things about constellations. Pardon me, guys. Oh, here we go. Okay. Let me give you a heads up on where we're going with this. Okay. Function F579. This is a three-dimensional picture of your local sky that is attempting to show you what the trajectories of stars look like as they rise and set in your local sky over the course of the night. You have a green disk, which represents the grass, and you're standing here. There's the North Celestial Pole. And these circles represent the diurnal tracks that stars make as they rise in the east, come up and cross your meridian, and then sink back down and set in the west. If you go out at night and you take a camera and you put it on a tripod and point it towards Polaris, well, first of all, you have to know how to find Polaris. So probably most of you have seen the Big Dipper before. The Big Dipper is part of the constellation Ursa Major. This is the Big Bear, and the handle of the Big Dipper is the tail of the bear. The spoon part is the butt of the bear, and then he has some other claws and a snout and stuff, but those are fainter stars that are harder to see. We refer to the front two stars of the Big Dipper as the pointer stars, because if you go out at night and you kind of make a line through those two stars, that line points almost towards Polaris. So this is an old observer's trick on how you can find Polaris in your local sky. You use the pointer stars to identify it. If you're in a very dark sky, like if you're out in Block Island or down at Ninigret State Park, you might actually be able to see the Little Dipper. Polaris is the tail star of the Little Dipper, and it kind of bends backwards. Some people say that the Little Dipper and the Big Dipper pour back and forth into one another. I'll tell you that from my location in downtown Providence or from the observatory in Warwick, I can clearly see Polaris. It's not very bright. And I can see this star, which is called Kochab, and I can see this star here. But these stars, I cannot see them from downtown Providence, and I can't see them from the observatory in Warwick. Some of you may live in a darker sky than me if you live in South County. Go ahead and challenge yourself. See if you can find the Little Dipper. That would be a cool observing challenge. Now, the point I'm trying to make here, besides showing you how to find the North Star, by the way, is the North Star directly over your head? Is the North Star at the zenith? Yes or no? Hell effing no. Not unless you're Santa Claus and you're living at the North Pole will Polaris be over your head at the zenith, okay? So just I wanted to make sure we didn't have that confused. Let's say you took a camera and you pointed your camera towards Polaris on a tripod and you took like a long exposure photograph. Over the course of the night, you would see stars seem to rotate and circle around Polaris. Actually, if you notice in this picture, Polaris itself is, this is Polaris here. You can see that Polaris itself is actually orbiting a little bit. What does that tell you about Polaris? Why would Polaris actually be circling around a little bit? Maybe I'm asking this question not in a very cool way. I was expecting Polaris to be there, but Polaris is actually there, which must mean what? It must mean that I've lied to you somewhere. What's the chat saying? Yeah, Devin, but could you bust? All right, Devin's made a good stab. He said it's not perfectly at the point where it appears stationary. Could you maybe use one of your $10 vocabulary words to say that better, Devlin? Or I'm sorry, there's Devlin and there's Devin. Jesus Christ, this is confusing. By the way, there's also like 6 Camerons. Make sure you give me your last name when you write me emails, okay? No Blackhole. Okay. All right, listen. Here's the answer I was looking for. I guess. All right, no, Devlin, that'll be even more confusing. Okay. Um, the fact that Polaris rotates means that Polaris must not be exactly at the north celestial pole. This dot here, well, that dot there, that's the north celestial pole. Polaris deviates from it by about half a degree. But, you know, we can lie to ourselves. For all intents and purposes, we pretend like Polaris is at the north celestial pole. Some stars are so, most stars kind of rise in the east and set in the west. But here's another, there's a cottage industry of taking pictures like this. Now, in this picture, we can see an example of what are called circumpolar stars, and we could in the last picture as well. Circumpolar stars are stars which lie so close to Polaris in your local sky that they never rise or set, but they merely circle the north celestial pole. Not every star in this picture is circumpolar. Why don't I head, this picture looks cool, but let's go back here. For example, this star here is circumpolar because it does not go below your horizon. This star here is not circumpolar because it will set below your horizon, okay? So circumpolar stars never rise or set. Back to our drawing. The north celestial pole is a fundamental point on our local sky. I'm going to put it over here. The last thing that we have to draw on our picture is the celestial equator. And this is going to require some good art skills. We need to make a horseshoe that goes through the southern sky that is at all points at a 90-degree angle to our north celestial pole. So the way I'm going to do this is I'm going to kind of make the best right angle I can. And I'm going to make a dot, a dash up here. And now I'm going to try to draw east to west, cutting through that dash. This is the hardest part for me, okay? Something like that. Label this CE for your celestial equator. The celestial equator, which a moment ago I defined as the projection of Earth's equator onto the sky, cuts through your local sky in a horseshoe that runs east to west. And in Rhode Island's case, it cuts through the southern sky. This is another fundamental position of the celestial sphere. So the celestial equator. Taken together, the zenith, the horizon, the meridian, the north celestial pole, and the celestial equator make up the 5 fundamental positions of your local sky. And these are new vocabulary words that I am going to employ to describe how stars move through our local sky. You need to be familiar with these 5 terms. I'm just going to give a second here to let you catch up. I'm going to have to erase this beautiful picture, so does anyone need another second? All right, you're all good? That's nice. All right, I'm erasing. It's time for us to learn celestial coordinates. We are going to need these to do our lab today. You may not find this a particularly riveting or exciting part of our lecture, but believe it or not, it's one of the more useful things I have to teach you. Many students who've taken my class end up developing an interest in astronomy. Some even get their own binoculars and telescopes and spend time out observing. The stuff that you learn here is helpful because it'll help you orient yourself in the sky and understand how it's turning. So this is cool, practical stuff that you can put to work, or you can put to use for you immediately. We are going to require 3 coordinate systems in this class to have the ability to describe stars in our sky. 3 coordinate systems. And this is going to take the rest of our day. The first thing, this is just a little top-down view so you can see where we're going. We're going to need to review geographical coordinates. Geographical coordinates help you locate yourself on Earth. As you may have gotten the sense of, where you go on Earth, where you are on Earth, will determine how stars move through your sky. The path of a star through the Rhode Island local sky is totally different than the path of a star at the North Pole's local sky or at the equator's local sky. So we need to kind of review where you are on Earth. Then we're going to have 2 coordinate systems for stars. We'll have something called the horizon system. The horizon system is a simple coordinate system that you can use in your local sky. And we're going to need a more advanced coordinate system called the Equatorial System. That helps you locate objects on the global sky or on the celestial sphere. All right. Can I erase? Geographical coordinates. They help you find your place on Earth. They use, let's remember that all these coordinate systems, take a note here, are angles. So everything we've done is going to tie in here. You've learned about angles so that you can understand these coordinates. Geographical coordinates use 2 angles, one called latitude and the other called longitude. And the goal is to help us locate ourselves on this rotating, spinning ball we call Earth. I'd like to point out that if Earth spins on its axis, there is a natural symmetry point, the equator, which divides the Earth into a northern and a southern hemisphere. The equator seems like it might be a good line for us to begin one of our angles, and that's latitude. Latitude are the number of degrees north or south of the equator. Wow. Degrees north or south of the equator. For example, if you wanted to talk about the North Pole, the latitude of the North Pole would be 90 degrees north. And I'd like to point out that one needs to specify the angle and the direction unless you're at the equator. That's kind of a big deal. In the case of Providence, Rhode Island, which is pretty close for anywhere in Rhode Island, the latitude of Providence, Rhode Island is 42 degrees north. This is a pretty good thing for you to know. You're supposed to know your latitude on Earth. It means you're classy and educated or something, right? That's kind of nice. We're roughly, 45 degrees is half of 90. So you can think of the state of Rhode Island as being just about halfway up the globe. That means we're a pretty good arbitrary location on Earth to describe the motions of stars. Now let's deal with longitude. Longitude, which run longwise from north to south, divide the Earth up into a bunch of tangerine slices that run from the North Pole to the South Pole. They measure east to west. The problem with doing this is that unlike the equator, there is no natural symmetry point or no natural starting point to begin your longitude. Humans had to invent the 0th degree of longitude. And let me show you how they did that with a slide here. I want to go back a little bit. They decided to make the 0th line of longitude a line that ran through the front door of the Royal Greenwich Observatory, which is just outside of London, and the so-called prime meridian runs right through the front door of the Royal Greenwich Observatory. And this line is going to divide the entire Earth into an eastern and a western hemisphere. Now, what's cool about that is you can actually go on vacation and you can travel to England and visit the prime meridian, visit the Royal Greenwich Observatory, and then you can stand with 1 foot in the western hemisphere and 1 foot in the eastern hemisphere, and you can take a selfie and for the gram. You know what I'm saying? And this is a thing that people like to do for fun. As a matter of fact, one of my former students, after taking my class, visited the prime meridian and brought me back a present, my very own prime meridian pencil from the gift shop. This is a treasured item. No one gets to borrow my prime meridian pencil. Okay, so feel free to send me presents when you too visits the Royal Greenwich Observatory and you get to see the prime meridian. That's how we're going to define longitude, okay? It's measured as degrees, measured degrees east or west of the prime meridian. Now, as a classy example here, the longitude of Providence, Rhode Island is roughly 71 degrees west. Couple of thought questions before. Oh, go ahead. Ask your question, friend. What?
Do you always measure longitude in degrees west instead of east?
No, you can. It's bifurcated. You shouldn't think of it like that. Some of our coordinates will be like that, whoever I was talking to, but in the case of the longitude, it's even Steven. You just decide if you're closer to the eastern hemisphere or the western hemisphere, and you measure 0 to 180, right?
Thank you.
By the way, whoever that was, on other planets, they do it that way. Like for geographical coordinates on Mars, they either have western or eastern based ones. So that idea that you had is actually a pretty good one. It's just that geographical coordinates developed so long ago that it has its own kind of thing. And the thing is to measure east and west. I'm not saying that very well, but I think you understand. Hey, does anyone know what the line opposite the prime meridian is called? The prime meridian cuts through, I think I need to go to show and tell mode here.
I think it's supposed to be the international date line.
Very good, Christopher, the international date line. And so let me just explain what we're talking about here. If you check this out, the prime meridian runs through Greenwich, England, but also through a bunch of other countries. But on the backside, we don't call it the prime meridian. We call it the international date line. And there's some cool things to mention about this international date line. The international date line is where we define the boundary between days on Earth. Let me say that better. It's where we have like Tuesday end and Wednesday begin. Because if you think about it, on a spinning Earth, can I just get a normal picture of the international dateline? On a spinning, why am I having trouble? Did I do something weird? Images. Okay. Whatever it was, I fixed it. Okay, so because Earth is constantly spinning, you kind of have to define where the day begins. And we define the beginning of the day as when the international dateline crosses the sun. When the sun is at the meridian, that's noon. So I guess the sun, when it's opposite the international dateline, that's the beginning of each day. And that means if you're a business person and you have to take a flight from Tokyo to Los Angeles, you might actually go back a day as you cross over the boundary between Tuesday and Wednesday. So that's kind of cute. You'll notice that the international dateline doesn't go straight, but it kind of wiggles around for political reasons. And if you think a little bit, there's some good reasons for that. You wouldn't want the international dateline to cut through different parts of a continent, right? Like here you can see in this picture, it's wiggling around Fiji and Tonga and American Samoa. It would be very annoying for the postman if it was Tuesday on one side of the street and Wednesday on the other side of the street. That would be unhelpful. So we actually have it wiggle around these bodies. I think that's another reason why the international dateline is structured where it is. It's kind of a very narrow range of longitude where you avoid cutting through any large continental landmass. Okay, so now you know about latitude and longitude. Good to know your own. Hey, what's the longitude of the North Pole?
0.
0.
It's not that you're exactly wrong. It's just that you're not exactly right.
Mr. Britton,
Yeah.
it's undefined.
Yeah, how did you know that, Chris?
Because you said that this was from last semester.
Oh,
And I was
okay.
there last,
Right. So that does that mean I taught you something and you remembered it? I can't
Yeah.
believe that's so cool. Okay, right. So hey, look, Chris is making a point, and whoever said 0, it's not that it's not 0, it's just that it's also 30 and 60 and 90. The reason why the North Pole is undefined is because every line of longitude runs through it. And in mathematics, we have a name for this. We would say that this point is degenerate. It's degenerate because it's multi-valued, or every single line of longitude passes through it. All coordinate systems on a curved surface will always have 2 degenerate points, but that's not harmful to us because if I tell you that my latitude is 90 degrees north, you know that I could only be located at one point on Earth, and that's the same place Santa Claus is located, at the North Pole, all right? On the other hand, if I tell you that I'm located at 42 degrees north, I could be in Providence, Rhode Island, or I could be in Springfield, Illinois, or Eugene, Eureka, California, or I could be in Osaka, Japan, right? 42 degrees north is not a unique point on Earth, but 90 degrees north is. So it's okay that there's no longitude here and there's no longitude down here, okay? They disappear at the poles.
So would 90 degrees south be the South Pole?
That's right. No cuts, no butts, no coconuts, all right? All right. Now that you've reminded yourself where you are on Earth, I'm sure you've heard of latitude and longitude before. It's time for you to start learning how we describe the positions of stars in our sky. And the first coordinate system is real basic and simple, although don't get cocky because you can get confused here pretty easily. Hold on, I'm just scanning the chat room. Okay, there we go. Okay, oops, that's gonna open up a hyperlink. Fudge, okay. This is the horizon system. We see a local sky with some observer dude. There's a star in the sky, and we're going to identify the position of that star using 2 coordinates. One is called altitude. That's how many degrees up from the horizon you are. And the other is called azimuth, and it's how many degrees along the horizon you are measured clockwise from north. Let's take some notes. Introducing the horizon system. The horizon system, I will remind you again, is your go-to coordinate system when you and a friend are standing in the same local sky. The angles are called altitude and azimuth, okay? Altitude is defined as degrees above, the degrees above the nearest horizon. So it's the degrees above the nearest horizon. Azimuth is defined as degrees along the horizon measured clockwise from north, okay? I had a method of describing this last time. What did I do? Let's grab a position on our local sky and let's try it together. I guess we could take this star for maybe this is too advanced here. Let's, do I have another picture? Okay. How do I want to do this? No, I'm sorry, guys. I'm having a little. I normally do a in-class exercise where I use a laser pointer and I have you get the altitude and azimuth of points in the room. That's actually pretty successful for training purposes, but I can't do that here over the screen. So we're going to pick this star, and you guys can see that this angle is its altitude, and this angle here is its azimuth. Do you think you guys, anyone out there, could give me a reasonable guess as to the altitude and azimuth of the star in this picture? What would the altitude of this star be?
The altitude is about, let's say, I don't know, 35 degrees.
Yeah, okay. If we go all the way up to your zenith, that's 90, right?
Yeah.
So it's kind of weird because this is in 3D, but you're saying, oh, maybe it's about a third of the way up. Okay. So you said 30, 35 degrees. I'm down. That's a very reasonable guess. Cool. What about
the azimuth? I would say is probably about 270. Or no, like
a little
maybe
more.
300.
Yeah, I'd say that too, because it goes 0 degrees, 90. This person knows their unit circle. Here's 180 degrees, right?
Yeah.
And then they were saying, well, that's probably 270s. Well, actually, this is perspective drawing, so I'm doing a crap job here. Undo.
It's okay.
You understand me anyways. You're thinking that's probably 270, so a little bit more is 300. Cool. Nicely done. What's the altitude of the zenith?
90?
What's the azimuth of the zenith?
360.
No.
Undefined.
Yeah. How'd you do that, Austin?
Because all of the planes, yeah.
Intersect.
Yeah. Arunsak got that too, right? If you're up here, let's go back to that other picture of the local sky that we drew a few moments ago. This is probably the best one to show. If you're located here, you're 90 degrees from the horizon, right? But all points along the horizon are equidistant in angle from that point, which is what Austin was sort of saying there, right? Okay, he understood it. All right, those are just some samples. We'll try a better example in a few moments. Let me tell you why the horizon system is good. Because it's stupid and it's easy, and any two people who are out at a telescope together can describe degrees up and degrees along the horizon from north. Oh, actually, can we do, I know what we should do. Let's put the 4 cardinal points here in terms of azimuth. Azimuth is very similar to direction, right? So due north is 0 degrees, right? Due east is 90 degrees. This is just for people who don't know their unit circle. Due south is 180 degrees, and due west is 360 degrees. Just writing that down could be helpful for you, okay? Azimuth and direction are kind of the same thing. So let me show you why the horizon system is nice. I'm going to show you guys a telescope that I think is kind of cool. It's a plane wave 1 meter telescope. Now, this is something that would just, you know, when I have wish fulfillment dreams, I imagine someone buying me a plane wave 1 meter telescope and observatory. That would be kind of cool. It only costs about $500,000. So if you have any rich friends that want to buy me a Christmas present, consider investing in a plane wave 1 meter telescope. Now, the plane wave 1 meter telescope, it uses a mount that's called an alt-az mount, an altitude azimuth mount. Let's see if we can find, there's a video here. I'm going to go to the images for a second of these guys operating the telescope sort of in the clean room there. Here we go. So this is just a quick YouTube video, if you guys can follow it here, showing them slewing around the plane wave 1 meter telescope. And I want you to watch the 2 directions that the telescope is moving in. It's moving in altitude and azimuth, okay? Wow, my internet is really slow right now. Okay. So you can see the fork arms here. Okay, there we go. You can see the fork arms, it can slew up and down in altitude from the horizon to the zenith. And then this mount, this part of the mount here is swiveling around in azimuth. So you can very quickly locate a star if you know its altitude and its azimuth. The way that might work is you might go to the telescope with your Grammy and you might say, Grammy, I need you to point the telescope at the Orion Nebula. And Grammy's going to say, I don't know where the Orion Nebula is. And you say, well, that's easy, Grammy. You got to go due east is your azimuth, and then go to an altitude of 45 degrees, and you can slew the telescope up, and there's the Orion Nebula. What's irritating about the horizon system is 2 things. Stars are constantly rotating as they travel through your local sky. So as you can see in this picture here on slide 79, during the course of the night, a star will constantly change its altitude and azimuth as it rises in the east, gets higher and higher in your sky, crosses the meridian, and then sinks somewhere back down in the west. So your telescope needs to constantly be changing its altitude and azimuth to track an object. Now, in the old days, that was really annoying because you had to do that by hand. But today,
there's shit everywhere. Like shit?
You know what kind of shit is everywhere, Ty? Your inability to mute your audio. Where are you? Okay. Hey, Chatty Cathy, mute yourself. All right, I gotta find you. All right. Thank God they gave me the power to mute people. All right. Anyways, as I was saying, a modern telescope has a computer built into it that can track. You just had to go there, Austin. Okay. Right, okay. I'm really glad that people watching the video later can't see this chat. Okay, so the telescopes constantly need to be moving. This telescope right here, this crummy little telescope, uses an altitude and azimuth mount. So you can see that here I'm pointing to the horizon. There I can lift myself up in altitude. There I can swivel in azimuth. One of the most irritating things you discover when you first buy your own crappy little telescope is you spend all this time wiggling and adjusting it and pointing at the moon, and then you want to show your friend and you want to say, hey, come check out the moon. It looks pretty cool. But by the time your friend walks over and looks through it, the moon has actually drifted out of the field of view. Another reason that it's difficult to use the horizon system is that if you discover some really cool object in space, like a cool galaxy, and you want to call it the Austin galaxy, if you try to call your colleagues in other places, like in Japan or in Moscow, if you try to tell them where that galaxy is located, just because it's 30 degrees above your horizon does not mean it's 30 degrees above the horizon in Tampa, Florida, or in another country. So what we kind of need, the horizon system is good when you're with your friend at the telescope, but what we need for professional, that's why, Austin, we use the equatorial system. And the equatorial system is a different concept. We're going to actually make a coordinate system that is fixed to the rotating sky. Basically, what we're going to do is we're going to reinvent latitude and longitude for the celestial sphere. And that means once you pick a star or a galaxy, it will keep fixed coordinates, and you can tell everyone exactly where the Austin Nebula is, and they'll be able to find it. The problem is equatorial coordinates are a little bit more confusing than the horizon system. I'm going to do the equatorial coordinates. I have some tests. Guys, remind me that next time I want to play a little game that's going to test your ability to do these coordinates. But I think all we've got time for is to introduce this equatorial system. So let's take some notes. Okay. So introducing equatorial coordinates. These are for the global sky. And they're the same for all observers everywhere. They use two angles. One is called declination. We sometimes abbreviate it as dec. Sometimes we use the symbol delta for it, declination, okay? And the other one is called right ascension. Astronomers usually just call right ascension RA because they're lazy bastards, myself included, all right? Now, just to help you kind of understand where I'm going here, this coordinate is kind of like latitude, and this coordinate is kind of like longitude. And here are the definitions. Like latitude, declination will be measured above or below the celestial equator, but we're going to use positive and negative instead of north and south. Declination is defined as degrees plus or minus from the celestial equator. Okay? Picture would be nice. This is a picture from your book. It's okay. Sorry guys, I've lost my place here. Here's a famous star called Vega. You start at the celestial equator. You're going positive above the celestial equator, and it's located 38 degrees and 44, what are these things called again? 44, whatchamacallits?
Arc seconds.
Arc minute.
Arc
seconds.
minutes. Arc seconds have the double apostrophe. This is 44 arc minutes. What fraction of a degree is that? I want to see whose brain is on today.
What does it say under? I can't see it.
I'm sorry,
160.
could you say that question again? Because I couldn't make you out.
Sorry.
I just needed to see the board behind you. I'm sorry.
That's okay. Okay. Right ascension has a really weird definition. I'm going to give it to you, then I'm going to try to explain it to you, all right? So right ascension is defined not in degrees east or west. We're going to measure right ascension in hours. That's going to sound kind of confusing. Right ascension is defined as the hours and minutes. So in hours and minutes, measured eastward from the spring equinox. Now, if I were you and learning this for the first time, I'd be thinking, the hell you say? What the hell does that mean? I can explain it to you. We just got to do it nice and slow. Now, you were probably expecting me to measure right ascension in degrees, the way I measure longitude in degrees. But I do not have to do that. And here's why. Think of a spinning Earth. It rotates in 24 hours. And it will spin through 360 degrees. Everyone take out your Casio calculators, which have not gotten any play yet today. And I want you to just humor me and divide 360 by 24. What do you get?
15.
Exactly. And let me show you the units here. 15 degrees per hour. You know, it's not random. It's not a coincidence that those two numbers divided perfectly into 15. The hour was designed this way by ancient Babylonians who invented the hour. They divided the rotation of the sky up into 15-degree wedges, each which are called an hour. So they intentionally, Babylonians intentionally divided the sky up in such a way. Hours and minutes, they go back thousands of years, okay?
Is that sarcasm or is that actually how they did it?
No, I know I have a streak for that, but I'm being 100% honest and legitimate here. Now, what that means, if you think about it, in astronomy, there's this weird conversion factor that should not make any sense, but it makes perfect sense in astronomy. And it goes like this. 1 hour is equal to 15 degrees of sky rotation. So I can measure the positions of stars in degrees, but if I'm measuring along the right ascension axis, along the rotational axis, I can also measure it in hours. And it's hard to explain right away, but this turns out to be a really useful thing to do. It actually makes things easy when you're out at a telescope. Unfortunately, somewhat hard to learn. Next, I want to talk about the spring equinox. Where did we measure our longitudes from on Earth?
Prime meridian?
Right, and I want to use this globe to show you why I can't do that. I've just taken this ring, which is probably hard to see, and I've aligned it with my prime meridian, and you'll notice that as Earth rotates 360 degrees, 24 hours, 15 degrees per hour, the prime meridian sweeps through different locations on the sky. And that's not helpful. We don't want the 0 point to be moving. We had to pick a point somewhere on the celestial sphere to start measuring from. Now, you guys remember in your last lecture, you learned about the 4 key points in Earth's orbit called the fall equinox and the spring equinox. And those were originally introduced to you as points in Earth's orbit. But if you think about the celestial sphere centered on Earth, the 4 key points in Earth orbit can be represented as dots located along the ecliptic definition number 2 of the ecliptic, which I bet everyone's forgotten. What's the second definition of the ecliptic? The purple line that you see here. What does the ecliptic mean? Someone enlighten me with their vocabulary skills.
It means that it eclipses the Earth.
No. The ecliptic is not related to eclipse. Well, not-
Path of the sun against the background of the stars.
right. Austin for the win. So listen, what Austin is saying, friends, is that this purple, okay, clear. Maybe I should choose a purple line. This purple line here, this is the path that the sun makes over the course of the year. This is where the zodiac constellations are. Seen from an Earth-based reference frame, the spring equinox, the summer solstice, the fall equinox, and the winter solstices, these are actual points on your celestial sphere. In fact, the spring equinox is the point where the celestial equator intersects the ecliptic, or one of the points. And these aren't just dots on the celestial sphere, they're actually points in your sky. Every day, the spring equinox rises and sets in your local sky. It's an empty dot located somewhere in the constellation Pisces. Normally, you don't notice it because usually there's nothing there. Likewise, there's usually nothing at the summer solstice at the foot of Gemini, except once a year, one day per year, a special astronomical object will appear at the spring equinox. Can you guess what it is? What is the special astronomical object that appears once per year for one day only at the spring equinox?
The sun?
Who's smart? Was that you, Christopher? Damn it, why you gotta raise the bar so high? Yeah, that's right. That's where the sun's gonna be, Christopher. Do you know what day it's gonna be there?
March 20 something.
21st, 20 something, right. And let me tell you, Christopher, around June 21st, the sun will be at the foot of Gemini. That's the significance of these points. They're showing you where the sun will be at key times throughout the year. I can base my coordinate system off of this if I want to, and I want to, okay? Clear all drawings. So for instance, if you guys dial it back a couple of pegs here, here's our star Vega, okay? And the star Vega has a right ascension of 18 hours and 35 minutes. I don't like the way your book wrote that here. They wrote it like slobs. Normally the way people write ascensions is they write it like a military clock. 18 hours and 35 minutes. And what that means is you start at the spring equinox, you go eastward, which is counterclockwise, you go 18 hours around the clock, which is right about here, and that's your right ascension. Remember that right ascensions are like tangerine wedges. It's hard to see in this picture here, but right ascensions are tangerine wedges that slice through the sky. In other words, right ascensions run from the north celestial pole through the equator to the south celestial pole. I don't know if you guys can see this in my camera, but can you see these lines here? You're going to be using these in your lab. There's 14 hours of right ascension. There's 15 hours of right ascension. There's 16 hours of right ascension. Each of these wedges is 1 hour or 15 degrees on your sky. This is going to take a little bit of getting used to. With our last 5 minutes before we do lab, let's do a sample problem where we practice using declination and right ascension. I think this will help us for our lab today. So I need to erase. Hopefully there's no objections to that. Here's the in-class question. Find the right ascension and declination of the 4 key points on the celestial sphere. And the 4 key points are spring equinox. That'll have a right ascension and a declination. The summer solstice. Fall equinox. And the winter solstice. Now look, I know this is hard. That's the reason why I'm asking the question. But let's just take it nice and slow and let's see what we can do. I'm going to call up a picture that's going to help us here. Let's start with the spring equinox. That picture isn't necessarily the best. Let's use this picture here. Can you guys help me? I want to start with this point, the spring equinox, right there. The red dot. Can anyone give me either the right ascension or the declination of that spot?
Wouldn't the declination be 0?
Very good, Donovan. I like your moves. Donovan, can you walk through that logic for everyone else who might not have followed you? How did you know that point had a dec of 0?
Well, you said before the declination is the point that they chose to start from was the spring equinox, and it is the spring equinox. So it's
Hold on. I'm afraid, Donovan, that you might have mixed two modes up. They start right ascension from the spring equinox, but declination begins where?
Equator.
At the celestial equator. So anywhere along the celestial equator, positive is positive declinations and negative go down from the celestial equator. So Donovan, what I would have liked you to have said is, this
I got
is
it
0
right
degrees.
the wrong way.
Pardon?
I got it right the wrong way then.
Or maybe, I don't think that's what happened. I think getting it right is different than explaining how you did it. I think you're explaining how you did something is harder than doing it, okay? So the declination is 0 degrees. How about the right ascension? Let me see what the chat says here. Oh,
Up to 0.
yeah, but here, Arunsak got that too. Here, the right ascension is 0 hours and 0 minutes, and we write it like this. As Donovan was saying a moment ago, we measure right ascensions from the spring equinox in time, and you're on the spring equinox, so it's 0 hours and 0 minutes. Okay, that was the softball. Let's try an easy, and let's try a harder one. How about this point right here? What would be the dec or the RA of that point? It's okay if you guess wrong. You can shout it out, whatever.
I know that the right ascension is 6 hours, correct?
Oh, was that Devlin?
Yes.
I can recognize the timbre of your voice. I can't see your face. Anyways, Devlin, hell yeah. How did you know that was 6 hours? Can you walk us through that again?
Well, the
Oh,
solstices and the equinoxes are separated by quarters.
and how many hours is it around the entire sky?
24.
So half would be
12, and a
And a-
quarter would be 6.
nice. You're good. How about the declination, Mr. I know what's up?
That is where I have trouble, because would it be positive? It'd be positive, I know that. I just don't know the rest.
23.5.
Yeah, they show you the angle right there. This angle is 23.5 degrees. Okay, so we have our answer. The summer solstice has a right ascension of 6 hours. That's how I'm going to write it, okay? I'm going to use cell padding, as they say. And declination, positive 23.5 degrees. All right, let's see if we can crank out the others. How about the fall equinox? Over here.
$12 hours for right ascension,
Excellent. And declination?
0 degrees.
Yes. And Arunsak is following along too. Very good. Okay. So we'll write that down. And you can study this later yourself if you're, to try to understand what's going on. 12 hours, declination 0 degrees. How about the winter solstice? Can anyone just shout it out?
18 hours.
Yep. How about the declination?
Negative 23.5 degrees.
Negative 23.5 degrees. Nice. Listen, some of you followed me there, and some of you understood this. But I'm betting now, I bet there's a couple of people out there are going, what the fuck is going on? I already know that's happening, okay? So that's natural, but you do owe it to yourself to try to figure out what's going on. This is to help you. You can test yourself and try to understand how they got those numbers. And feel free to ask me a question if you want me to hyper explain something,
I understand the declination, and I understand how it what it means. It means obviously the degrees forward or backward from the celestial equator.
Could we say up or down rather than forward or
Up or
backward?
down, yeah, sorry.
That's fine.
But I don't understand how you were getting these measurements.
Well, the way we were getting it is by using the definition. If this here represents the celestial equator, can you see my globe, Devlin?
Yeah.
If I have a star there, it's on the celestial equator, so by definition, its dec is 0 degrees. Notice that you can see the measuring declinations here. For instance, if I go up to this first horizontal line, that's positive 10 degrees declination.
Okay,
Positive
okay,
20,
okay.
Positive 30, positive 40. So we were just looking at the celestial equator and seeing roughly how much above or below. Now the right ascensions, first you actually have to find the spring equinox, which you guys can see is
Located.
there.
Yeah.
And then we're measuring in hours eastward. So let's see, this is 1 hour of right ascension. This is all backwards. This is 2 hours of right ascension, 3 hours of right ascension.
Yeah.
Okay.
I get it. I was just having trouble with the degrees up or down. I get it now though.
So it's time for our lab now, students. And the lab will help with that, Devlin, because we're going to find the 10 brightest stars in the sky from their coordinates. This lab is really, really cool when you do it in person in small groups. And it's just, and Chris knows because Chris has had the pleasure of having me live in class. So this is a really fun and useful lab. It's going to be tough. We're going to kind of do it together using my phone as an eyeball. It's not going to be ideal, but COVID-19, we got to do what we got to do. I have a couple of announcements to make that I really should have made at the beginning of lecture, and I forgot to, but maybe those people in the night class end up just fast forwarding to the lab. So let me go over here to the lab room and let me make some announcements about submitting work and stuff. Okay. So here we are. I'm going to need my phone for this. And here, I just saw another milk crate. Okay, this will be fine, actually. Okay. I've got my celestial sphere that we're going to use right here, okay? And I've got my worksheet. But let me start by making an announcement about grading homeworks and stuff. Yesterday, I had the pleasure of grading 160 homeworks, okay? Now, that wasn't fun, all right? That wasn't fun even a little bit. And I really just need you guys to work with me on the homeworks. For the most part, everyone did a great job. I discovered something last Thursday, which is at the end of lab, I've been for the first couple of times sitting around with everyone. Yes, Devlin, luckily there's wine in the house, okay? So anyways, after class, I've been kind of sitting there with you guys for the first couple of times to see how the uploads look. And last time that added an extra hour to the recording. I'm still willing to do that today a little bit, but I need you guys to remind me to stop the recording, because what happens is that adds another like 3 or 4 gigabytes to the file. And I don't have a good video editor, so it ends up screwing up the night class because I have too large a file. So at the end of lab, if you want to see how your work is being submitted, fine, but I should stop the recording first. And I shouldn't stay on too much longer because I can't start rendering the video until I stop. It doesn't render the video until I end the session with you all. Do you see what I mean? In other words, I can't spend an hour checking out your homeworks, not because I don't want to or I don't have the time or the inclination, but it messes up the time it takes to process the video, and I need to upload it to YouTube before the night students start to watch it. So you just have to trust me, there's reasons besides pure selfishness for this. The second thing is, most of you did upload the work in a nice, easy to view preview, but some of you still have the hyperlinks with the JPEGs, PDFs. One person submitted a movie file to me. I can't look at that, so they got a 0 because I can't see it. I don't want to give you a 0, but I need to be able to see your work. So please try to make it so that I can see the preview, because clicking on even the hyperlinks, it takes too much time. So please make sure that you can preview it in a box. By the way, some of you had the bloody things sideways. Not helpful. Please rotate your picture. Just figure it out, you know? I know it's different for everyone, but try to figure it out. Please do your best. If I can't read your homework, I'm gonna give it a 0. Secondly, this is about turning in late stuff. When I had smaller classes, I could wiggle around a little bit with people who were submitting late assignments, but not everybody in this class turned in their homework in their lab, okay? I have to close it out like today. If you didn't turn in your homework 1 and your lab 1, that's it. And that's because I can't go, you know what I'm really scared of next week? All those homeworks and labs and then people starting to submit late stuff, I'm gonna lose my damned mind. I can't do it with 168 people. You see what I mean? So you've got to get your homeworks and labs in by the weekend when I grade it. Do you think all of you can handle that? Most of you that I'm looking at right now are people that did it right because you did it with me. I'm talking to all you people out there in the after party, okay, at night. Get your damn shit in on time. And by the way, I have to do verification of enrollment this weekend. Any student who has neither submitted a homework nor a lab is going to be automatically dropped from this course. And I'm not going to be in a mood to let you back in because I've got too many people as it is. So I kind of have to be tough. That's the stakes are raised. 160 people is like a rock show. You know what I'm saying? So I have to have some hard rules here. So most of the people that I'm looking at, Austin and Donovan and Caroline and Devlin, I'm pretty sure you guys got your homeworks and labs in, right, Chris? Sometimes people even have trouble with submissions, but I can't let you extend it to next week. So today I'm gonna deactivate homework 1 and lab 1. And this is the, okay, Devlin, WTF. Okay, so let's say you screwed up. Tell me how you're gonna unscrew up right now. How are you gonna unscrew this up? Like you've got some work to do after lab, don't you? Or you're gonna be sucking some zeros for the start of the semester. That's right, Devlin. So when this lab ends, you're not gonna go play. You're gonna open up those things. You're gonna fast forward to the homework in the lab. You're gonna do them and submit them because tonight By the time I start drinking wine, the shits given are going to drop to 0, and I am going to deactivate homework 1 and lab 1, and that's it. So I'm giving you a little bit of wiggle room this first time, Devlin, okay? Can you handle this? All right, cool. That's what I want to hear. Thank you. Appreciation. All right, so I'll give you guys until the end of the night, till like midnight tonight, to last call for homework 1 and 2, or lab 1 and homework 1. Okay, now that we've gotten that out of the way, I hope you all remember this and take that seriously. So I'm going to do grading by the weekend. I need those things submitted. Let's get to business. Let's do lab number 2 on celestial spheres. And work with me here, guys.
There's no 5-minute break?
Do you want a 5-minute break?
Just 5 minutes.
5 minutes. You got it. That'll give me a chance to get some things together here. Okay, 5 minutes. I'm going to pause. Okay, friends. Let's try to get back into it here. I know that wasn't much of a break, but the labs are a little shorter than the homework sessions, so we do want to get it done. I'm going to see if I can share my phone screen. That's going to be very important here. I had trouble doing this the other day, but oh my gosh, it's making me reinstall the plugin. Yeah, Devin is asking me about cool apps that you can use for the sky, and I can actually show you one now that I'm trying to share my screen. Screen mirroring, Zoom be Britain. Okay, this is going to work. Can you all see my phone here? All right. There's a couple of different apps. The one that I like that's actually gotten worse over time is called Night Sky. I got a couple of different ones. Let me see here. My phone is like really disorganized. Come on. There we go. This one, Night Sky 2, is kind of rad. I think I paid $3 for this. And what's cool is I can hold it up to the horizon and I can see which stars and planets are overhead. There's a whole bunch of apps like this. Look, Venus is up right now. You know, this is such a cool app because if you're just out there and you see a bright object and you're not sure if it's a star or a planet, you can identify some of the brighter stars in your sky using this app. So there's Night Sky 2. There's actually probably a better one than this. You guys should try and check out a couple and see. Notice the sun is up right now, right? So I use Night Sky 2. Just sometimes it's helpful if I'm like, oh, what's the name of that star? I forgot the name of it. It helps you learn your constellations. It's very cool. It's very nice if you can have one that lets you control the limiting magnitude, meaning like how bright the stars are, because you don't want to overwhelm yourself at first. Okay, let's get rid of that app here. Woo, look at all these things. Okay. Let's go to my phone and let's take a look. This is how we're going to navigate through our lab here today. You can see I've got the celestial sphere set up. I probably need to work on my illumination a little bit because it's a bit dark. So let me open up the blinds here. That looks a little better. Actually, let me get this one too. Okay. Okay, that should make things a little bit easier. Ooh. Oh, damn it. We don't want to do that. Okay. This ought to make things a little bit easier to read. Sorry, guys. This is going to be a little kooky at first. Let's go ahead and let's fill out our sheet here. As you guys know, at the top, we should always put our name. You should also put, you guys are AS1020. And I need you to put your lab section here, okay? So if you're in 001, do that. Or if you're in 002, or if you're in the night class 101. By the way, every time you send me an email, always say, hey, this is Joe Bob, and I'm in Astronomy 1020 section 002. If you don't do that, it's almost impossible for me to like answer your question, okay? Okay, so check out what we've got here. In the first category, hold on, let me check the chat. Okay, no doubt. Okay, all for the gram. All right, you can see the coordinates of the 10 brightest stars in the sky. These are the most famous stars in our sky. And we're going to find the name of the star and the constellation. Now, do you guys remember how many constellations are on the celestial sphere? I taught you that at one point. How many? Someone's chatting here.
11.
13 is for the zodiac constellations. There's many more than, no.
Wait, what was the question?
How many constellations are there on the total celestial sphere?
It was 88, right?
Yeah, who said that? Who's good?
Reardon?
Oh, Reardon. Yes, Reardon. I like your moves. Okay, you remember things. I like you. Okay, so there are 88 constellations. Now, constellations are more than just the stick figures on the sky. For instance, here, let me get a cue card to help reading this. Where's the hole? Okay, hold on. I'm upside down. That's not helpful. So if you have a constellation like, let's find a nice easy one to look at. Lacerta is, here's a constellation, or maybe, I don't know. Here's one, Perseus, which is a helmet. You can see that there's kind of like a stick figure to the sky, but the constellations are actually areas or boundaries in the sky. And these dotted lines mark the boundaries of the constellations. Just like if you were to throw a dart at a map of the United States, you'd have to be in one of those 50 states. If you throw a random dart, the United States is gridded out into states. So is the celestial sphere gridded out into 88 constellations. Now in this sphere, the names of the constellations are in blue. The stick figures show hard lines in between the stars. The names of the stars, here's Alpharats. The stars are in black, but the boundaries to the constellations are these dotted blue lines, which you see here, okay? So what we need to do is we need to find the name of the star, and we need to find the constellation name based on these coordinates. Let's start with our first star. 6 hours and 43 minutes, negative 17 degrees. So let's see if we can find 6 hours here. I'm going to use my cue card. So here's 6 hours, right? And there's 7 hours of right ascension there. Where would 643 be? I need more hands, damn it. Where would 643 be? If this is 6 hours and that's 7 hours, where would I find 643? It looks like I've got some tick marks here, right? Let's see. If I break an hour into 3 wedges, what's an hour? What's 60 minutes divided by 3? Could someone talk to me and make me feel like I'm not
20.
doing
20.
Okay. So the big tick marks are 20 minutes, if you can see the big tick marks. The little tick marks are 4 minutes, I believe. So if this is 6 hours, that first tick mark is 6:20, 6:40, and the tick mark after that is 6:44. So roughly here, this is where 6 hours and 43 minutes is, right there, okay? What's our declination? Shout to me.
Negative 17.
It says positive on my end. Or actually, it doesn't have a degree on it on my end.
Did you download the document or the PDF? The .doc or the PDF?
I have no idea.
All right, hold on, guys. I realized something happened here. On Blackboard, okay? I don't want to stop using my phone here because sometimes it doesn't work that well. So I've got to stay in phone mode here. On Blackboard, I provided you guys with 2 different versions of the lab. notice that for LAB2, I provided LAB2 celestial spheres docx in celestial spheres PDF. The PDF one is perfect, but some people don't have a printer, so I thought I'd provide you. Okay, get out of here. You can see here in the PDF version, it's negative 17 degrees, okay? All right, so the document version, I think, is messed up. Who said they don't have the negative 17?
That was me.
Who's me?
I'm pretty sure I downloaded the PDF version, though. It's Kate.
Oh, okay, yeah. Hold on, this is the PDF one here. Look, no, you downloaded the document one, because look, Kate, the negative is missing.
Oh, I'm
So-
sorry. I added it in.
The way this happened, Kate, is I was trying to help students last semester who didn't have a printer by providing the Microsoft Word version that they could fill out online, but I didn't realize at the time that it would mangle the negatives and positives. So Kate, if you already have it printed out, just add the negative manually with your, yeah, okay, you can handle this, right? Where were we? So 6 hours and 43 minutes, minus 10, minus 20, back a bit. What's our star? Can you guys read that?
Sirius.
And the constellation must be, let's look around here. Ooh, what's the constellation?
Does that say Canis Molar?
Major. Canis Major is the big dog. Sirius is the brightest star in the sky. It's known as the dog star. So our star is Sirius. I know it's all backwards, and it's, sorry, Canis Major. Okay, one of the reasons things are written backwards is you're supposed to like look through the globe and then use a baffle on the other side so that you can read the names of stars. That's supposed to reproduce the curvature of the sky. But because we're doing this weirdly on my phone, it'll kind of be easier just to kind of read stuff backwards. Let's try to move a little quicker. I'm going slow here. 737 and positive 5. So here's 737. You know what? You know what I need, guys? I need tape. Hold on a second. All right. I'm going to do a thing here. I need to add some tape to this. This is still a work in progress here. You guys seeing this? Okay. Get out of here. Okay. So 737, there's 20, there's 40. 4 minutes before should be 36. So we'll start here. What's the declination? What's the dec?
Positive 5.
There's our star. Procyon and Canis Minor. Okay. 2040 and positive 45. All right. So let's go around here. Here we can see 20, 21, 2040 is here. And now we've got to go up 45 degrees. Positive 10, 20, 30, 45. It looks like our star is Deneb, and the constellation is Cygnus. Okay. 1948, positive 09. So we'll go to 19, 1920, 1940, 1944, 48. Positive 09 is up 10 from, this is 10, so positive 9 would be about there. Our star is called Altair, and the constellation is Aquila. Aquila is the eagle, and Altair is the eye of the eagle. Ooh. Next up, 513, positive 46. Take a note here. Okay. This is kind of busy, so I'm going to get some tape here. Oh, sorry. So there's 5, and there's 6. Class, where's 513? Where do I go? I want to make sure somebody is following me here. This is 1 hour of right ascension, right? From 5 to 6. So if I'm at 513, I want to stay along the celestial equator, but how far do I go?
Want to go to that first tick mark that represents 20 and go like right before it, like that little tick mark before it?
I like it. I like what you just said. That's good. And now we got to go up positive 46. That's good. That means you guys are following me. I was worried about this. All right. So positive 10. The next line is positive 20, 30, 40, and 46 will be a little bit above halfway. We have the great star Capella, and Capella is in this constellation, Auriga, the herdsman. Okay. Next up, 513 minus 08. We're still at 5. 513 is in the same position. It's about, if this is an hour, a 1 hour wedge, 15 minutes is about 3/4 of the way. And then minus 8 goes almost down to negative 10. This star is the star Rigel. Rigel is at the foot of Orion. Next up, 1410 plus 19. Let's rotate here. Okay, this is a pretty good angle I've discovered. Okay, so there's 14. 1404, 1408 is really close to 1410. Once again, I want to start at the celestial equator because this is, for some reason, they gridded things out at the positive 10-degree declination mark. That can be a little confusing. So I want to be at 1408, but I want to start at the celestial equator. And I want to go positive 19. So plus 10, plus 20. What's our star? How do I say that?
Arcturus.
Arcturus. And that's in this constellation up here. Ooh. Bootes. It looks like booties, but it's Bootes. I believe there's an umlaut there. So, so that was Arcturus. And the constellation is Bootes, where I believe the second O has an umlaut. Not every day you get to bust out your umlauts, right? Bootes. Okay. $553 positive 7. 53 will be almost at 6 hours. Plus 7 brings us here. What do we got?
Beetlejuice.
Beetlejuice.
Betelgeuse. In what constellation?
Orion.
Orion.
Okay, 1627, negative 26. I'm sweaty. All right, 1627, negative 26. Let's rotate this around. 1624, 1628, and minus 26. Down 10, down 20, down 6. You guys know how to pronounce that?
Antares.
Yeah, Antares is anti-Mars. It's a famous red star that's confused with Mars. And we can't cross a dotted blue line here, right? So I lost it. Antares is actually down here in Scorpius. Okay, 1836 and positive 39. Last one. 18, 20, 40, 36 is one tick mark before, and positive 39. 10, 20, 30, 40, boom. We saw this star in our lecture today. The star is Vega, and the constellation is Lyra the Harp. Lyra the Harp. Okay. All right, let's take a good look at that. I've got a couple of things in mind for us to do next. Let's look at this. First of all, does everyone have all that good stuff? Okay, cool. Let's take a look at table 2, current planetary positions. To do this, I'm going to make use of a website. In the olden days, if you wanted to look up the positions of a planet or star, you would use a book called an ephemeris. And we have modern day ephemerises. In fact, I'm going to go to ephemeris.com. If I type in Sun to Sedna. At ephemeris.com, they show you the positions of the planets and the sun and the moon tonight. Class, why wouldn't the planets be printed onto the globe just like stars are? Does anyone know why they don't have the planets listed on the globe?
Because they move.
Very good. Who said that? Well, whoever you are, you're right. Planets are wanderers, and they drift with respect to the stars every night. Let's go ahead here, and let's grab the right ascension and declination of the planets from Mercury to Saturn. These are the 5 naked eye classical planets. I want you guys to write after me, okay? So we're going to do an RA and a DEC. These are for the planets tonight. So for Mercury, it's 1217. That's the right ascension. And the declination is basically -2 degrees. For Venus, it's 818 and positive 18 degrees. For Mars, it's 1 hour and 50 minutes. Mars's declination is positive 7 degrees. For Jupiter, we've got 1916 minus 22 degrees. Saturn, negative 21 degrees and 17 arc minutes. Oh, sorry. 19. I apologize. 19 hours and 50 minutes and negative 21 degrees. Can you guys see how these coordinates are kind of close to each other? You may have noticed, like if you looked at the sky last night, you can actually see Jupiter and Saturn next to each other in the sky. Jupiter is the really bright orange dot, and Saturn is just up and to the left. So these are actually going to be visible in your local sky tonight. Let's see if we can figure out what constellation each of these things are in using the technique we used from the last lab. So let's start with Mercury, 12 hours, 17 minutes, negative 2 degrees. Let's see if we can figure out what constellation Mercury's in. So here's 12 hours, and 12:17 is about there. And now we got to go minus 2 degrees. Oh, there's too much glare on this globe. This is kind of one of the tougher labs. If you notice, you're in this constellation, and that's Virgo. Next up, 18 plus 18 degrees. Wait, sorry, 818, not 18. Too many 8s. So here's 8. 818 is real close to 1820. And minus 2 degrees is there. Wait a minute. This can't be right. 818. Oh, I see. It's positive 18 degrees. I started freaking out because that's the constellation Hydra. Hydra cannot be one of the constellations that Venus appears in. Why? Why couldn't Hydra? Maybe I'm asking a question that you.
I think it's because, like, as Venus orbits the sun, it wouldn't pass through that.
Yeah, what constellations would we expect it to pass through, Mr. Smarty?
The horoscope constellations.
You mean the zodiac constellations?
Yeah, those ones.
Oh, okay, yeah, good vocabs. Okay, right. And when I started looking here and I saw Hydra, and I was like, wait a minute, Hydra's not a zodiac constellation. That's because I read -2 instead of positive 18. So here's 818. We'll go up positive 10, positive 20, and sure enough, we're in Cancer. That makes a lot more sense. Okay, Mars, 1 hour, 50 minutes, positive 7 degrees. Rotate over to 1 hour. 1 hour and 50 minutes is a couple of ticks off from 2 hours. And then I want to go positive 7 up to here. So we got to be careful. We can't cross that dotted blue line. Can you guys see that dotted blue line? We can't cross that. We got to follow this up here to Pisces. Pisces. Excuse me, class. I'm kind of dying here. All right, 1916, negative 22 degrees. 19 hours. 16 minutes puts me about a quarter turn from 19 to 20. Negative 22, minus 10, minus 22. I'm in this bloody constellation, which is Sagittarius. Yeah. So let's not misspell this here. ITTARIUS. Okay. Lastly, we have 1950 and negative 21 degrees. Okay. So 1950 minus 10 minus 21 degrees. And we're also in Sagittarius. They're in the same constellation. That makes sense because they're located near each other in the sky. You know, class, these constellations may not actually be the constellations the planets are located in tonight, Do you see this globe here, this very cool celestial sphere? They don't make these anymore. This was made in the 1960s with what are known as 1950s epoch coordinates. Over time, you guys will remember that Earth goes through a precessional motion, which causes it, gravitational tugs between the moon and the Earth, cause the Earth to twist with respect to the celestial sphere. That causes the ecliptic to drift through different constellations over time. If these had been the positions of the planets in 1963, that's where the planets would have been. But in the intervening 50 years, there's just a teensy bit of a drift. So sometimes the planets will drift over into a new constellation. That's also important for your astrological sign as well. So let's play a little game here. It's called, Are You What You Think? Well, actually, no. Let's do one more exercise, and then I'm going to play this little game with you. We're going to do one last exercise on the next page. So I want you guys to have 3-4, and I want you to have this little chart here, okay? Table 3 shows positions of the sun along the ecliptic. We're supposed to move the sun to these random dates and figure out what the RA and the declination of the sun would be on those dates. Now to do this, I can use this little nubbin here to rotate the sun along the dates of the ecliptic. So you can see the ecliptic is a line here that has dates on it. Here's December, December 5, 10, 15, 20. Let me get that cue card out here. Here you can see some dates on the ecliptic. There's May, 5, 10, 15, 20, 25, 30, and so on, okay? Our first date is March 21st. So we want to move the sun. Wait, that's not going to work. Okay, we want to move the sun here. So there's March 5th, March 10, March 15, March 20. March 21st is there. What would you guys say are the coordinates of the sun on this day? What's the right ascension and declination of the sun right now?
0, 0.
Yeah. Doesn't that sound familiar?
That's the spring equinox.
Very good. Some people clearly remember it's 0 hours and 0 minutes and 0 degrees. Some people remember what we learned in class today. That makes me very happy. Let's move to June 21st. So here I am.
Isn't that the summer solstice?
Good. So what are the coordinates?
Couldn't tell you.
How many
Off the top of my head.
Well, we could do it empirically. How many degrees above the celestial equator does that appear to be?
23.5.
Oh, do you mean positive 23.5?
Yes, sir.
How about the right ascension?
0600.
Hours.
Yep.
Oh,
and
sorry, bro. You can go
there,
down.
6 hours. Oh, 600 hours. Very good. All right, cool. So we're doing this wicked fast, right? That's how we want to do it. Let's go to the fall equinox.
1200 hours.
Very good. Sorry, let me.
Zero declination.
Yep, and we're supposed to be right there. The little kid in, Bangladesh who made this didn't align it correctly for us, so whatever. So it's not a perfect alignment there. We gotta, okay. All right, so 12 hours and 0 degrees. Very good. Okay, December 21st. Let's move around here. All right, here we go. December 21st is right there on the ecliptic. Oops. And you guys already know what the answer is, right? How many degrees down are we?
Negative 23.5 degrees.
Okay.
1800 hours.
Good. Now, here's what I want to do. This is going to be our final act here. This works really well in the summer class when I have like 10 students because I can do it for everyone. But there's too many of you to do this for. What I want you to do here is I want you to write down your birthday. So watch me do this for me. Rather than write down today, let's cross out today. Let's find out if you're still the zodiac sign that you thought you were. So my birthday is 4/20. So I'm writing down month/day. You guys do the same, okay? Now, according to my zodiac sign, like, let's say I was an astrology smoker and I woke up every day checking my co-star before I brushed my teeth to find out if I was going to meet someone at the coffee shop or whatever the hell people do, okay? So in that case, I would be told that 4/20 is on the cusp, and I am supposed to be in Aries/Taurus cusp, sometimes Taurus, all right? So that's what it's supposed to be. Now, so maybe I'll put that under here. So, you know, sometimes people say it's Taurus, okay? But it's like an Aries-Taurus cusp. Now, let's go ahead and let's move the sun to the date of my birthday, okay? So here I am on April 20th. Bear with me, class. And you'll discover that the sun was on the cusp on my birthday, except if you look at April 20th, it's not on the cusp of Aries and Taurus. April 20th is now on the cusp of Aries and Pisces. So whereas I was supposed to be an Aries-Taurus cusp, now I've drifted to Aries-Pisces. So what's the truth about my zodiac sign? Why did that happen? Why, when I looked at this globe, why did I see Aries-Pisces instead of Aries-Taurus, which is what I'm supposed to be? Who understands why that happened?
Because the Earth drifts and it doesn't always end up like in the same exact place.
Yes, Kate, but can we have some fancy terms for this? What is that drift called? The drift is called, well, I don't know if I actually had you guys write it down. If you want to see a cool picture of what I'm talking about, where's Kate? Okay, there you are. If I go here, there's a cool Wikipedia page called Precession of Earth's Axis. Or maybe it's precession of the equinoxes, I don't know. But they have an axial precession on Wikipedia, has some really jazzy pictures. So I like this one here. Let's click on this and see if we can. One of these actually shows you, sorry, I'm doing my best, guys. One of them is a little animation. This is showing you how precession works with the top. Did I do the demo for you guys in class? Maybe at some point I should. So here you go. Here's a little animation. This precession of the Earth's axis tilt takes 26,000 years. When you guys look up your horoscope and co-star, they are basing your horoscope on Ptolemy's Tetrabiblos, published in the 1st century AD, like 50 AD. And that means it's 2,000 years old. 2,000 years is a significant length of time, so Earth will have drifted by roughly 1 month during that time. So let's try another example so that I can really drive this point home. Since I'm talking to Kate, Kate, what's your B-day, Kate, month and day? Get it for Kate. I can't do this for everyone, but I'll do it for a few of you that are sharing video. Kate, what's your B-day? Sorry, you're muted.
Sorry, 7/6.
Okay. So July 6th. So let's go over to July. Oh, and what's your sign supposed to be? Like if you
Cancer.
Okay, so your sign supposedly is Cancer. Let's find out where the sun was on your birthday, okay? So let's move over to July 6th. Okay. This is where the sun was on your birthday. What constellation was the sun in on your birthday, Kate?
Gemini?
Yeah. So, Kate, the whole concept of your sun sign is that you're supposed to be a Cancer because the sun was in Cancer on your birthday, which is probably in the last 20 to 30 years, right?
Yeah.
Okay, but the sun wasn't in Cancer. It was in Gemini. So are you a Cancer or are you a Gemini now? What do you want
I
to
don't
be?
know. I feel like I can be a little two-faced. I might be a Gemini.
I think your astrology is a little two-faced. It's telling you that you're a Cancer, but instead you're a Gemini. Personally, when someone asks me what my sign is, I tend to tell them I'm like a Camillo Pardalis, or sometimes I tell them I'm a Vulpecula. And usually they look at me and they say, "What is that?" And I say, Vulpecula is a very exclusive zodiac sign. Not everybody gets to be a Vulpecula. Usually the conversation ends right there, and then they leave me alone at the bar to drinking my beer. Okay, so if someone asks you what your sign is, feel free to tell them that you're an Auriga, or maybe you could be a Lynx. Okay, all right. It doesn't. Anyways, when it's all bullshit. But anyway, let's try another one. Christopher, how about your birthday? What's your B-day?
January 22nd.
So 122. Do you know what your sign is supposed to be?
Aquarius.
By the way, this doesn't work for, sometimes people will still be in the constellation that they were born in. So he's supposed to be in Aquarius. Let's drift over to January 22nd. Sorry here. And we'll just do this for a few people. Just, oh, sorry, phones. I need a lot of hands to do this here. Okay. So you're supposed to be in Aquarius, but according to this, Chris, where's the sun on your B-day?
Capricornus.
Shit. So can you do me a favor? Anyone who I do this for, Kate or Christopher, write what your sign is supposed to be here. And then here I want you to put your real sign, okay? So you were supposed to be an Aquarius, but in fact, your real sign is a Capricornus, okay? Austin, you're my next little box. What's your B-day?
October 19th.
Okay, he's October 19th. And what's your sign supposed to be?
A Libra.
Don't you think it's funny how not a goddamn one of you knew what the ecliptic was, but every single one of you know what your sign is supposed to be through astrology? That scares the damn bejesus out of me.
Well, I've
okay?
never used the first word, in a pickup line, Professor. However,
hey, baby, were you along the ecliptic? You don't know.
I tried it once; it didn't work the same.
But
So
for the right kind of person, it could really be what it takes. Okay. Wait, I'm sorry. So Austin, what were you supposed to be again?
A Libra.
A Libra.
I'll let you know how it works out next time.
Okay, yeah. Actually, it's going to be like, get the F away from me, you damn nerd. Okay. So, but if they did like it, you'd know that was the one, okay? October 19th, okay? October, I have to be careful not to break this thing here. Okay. This is on the other side of the damn, all right, we're going to have to just do this as best we can. October 19 is there. Bum, 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 bum.
Wow.
Virgo, right?
I'm amazed.
So you can so by the way, if you try Libra and they say, "Oh, I really don't get along with Libras," you could say, "Actually, I'm a Virgo." Okay? You try that instead. Just tell them whatever they need to hear for your pickup line to work. Okay? So let's try one more. Stacy, what's obviously this would be fun to do with everyone, but we'll never end lab. So we'll just do one more for kicks. Stacy, do you know what your sign is supposed to be?
Taurus.
Okay.
421.
Oh, so you're close to
I'm
me.
the day after you.
Oh wow. Okay, wow. Okay, so we already know what's going on there. So you're supposed to be a Taurus, but you are now an Aries. We'll do one more, okay? Well, hey, let's wish each other a happy birthday. Okay, so anyways, Donovan, how about you? Donovan?
I might be a bad pick because I'm right next to you guys. I'm 426.
Oh, shit. Okay. Okay. Well, anyways, we'll do one more for fun. Emily, you want to give us yours?
Why don't we do Devlin since he thinks his birthday is so great?
Okay. Yeah. Actually, that's a great idea. Devlin, I like
December
that.
1st, baby. Let's go. Christmas.
Okay. What's your sign supposed to be?
I am a Sagittarius.
Oh, actually, this one might come out interesting. So Devlin, December 1st, who thinks he's so great, has a sign.
I'm just barely a Sagittarius, though.
Okay,
Like,
this is going to be interesting. I think Devlin's going to turn out to be really special. And I was hoping to get a December baby here.
oh, thanks.
Yeah, I'll tell you why in a second. Here we go over to December 1st. Ah, shoot. Hold on, guys. So here, oh, this is so perfect. Hey, whoever idea was to choose Devlin, that was a really cool idea. So here you can see December. There's December 5th, and there's November 30th. That puts Devlin right here. And Devlin thinks he's a Sagittarius, but check this out. We're going to follow those dotted lines, okay, up here. This is actually a pretty big constellation. According to this, what is Devlin?
And Ophi, I can't say that word.
Look, for a while, I used to pronounce it Ophiuchus. I suspect that's the real pronunciation, but the pronunciation key was Ophiuchus when I checked it on Merriam-Webster. So many people say Ophiuchus. I say Ophiuchus. I think here's the thing. I took 4 semesters of Latin, and I was bad at it. Although it's a super classy language. If you ever get a chance to take some Latin, you can hang out classicists, and they're really cool because they sit around reading Catullus and Seneca. It's kind of a classy language to learn. But in Latin, there were no soft C's like there are in American English. It was all K. You pronounce it like a hard C. So it wasn't Caesar, it's actually like Kaiser, right?
Kaiser.
So I think it's supposed to be Ophiuchus, but what do I know? Any case, Devlin, you are special. Your real sign is the 13th zodiac sign.
Oh, wow. Let's go.
Right? Ophiuchus was
Chosen
not
by
a
the
zodiac.
stars.
In 50 AD, because of the position of Earth in its precession, Ophiuchus was not a zodiac sign. It was not one of the 12 zodiac signs because the sun did not drift through Ophiuchus. But over the intervening 2,000 years, the slow precession of the equinoxes has eventually allowed the sun to drift into the 13th zodiac sign, Ophiuchus. So you are a very magical zodiac sign indeed. The sun was located in Ophiuchus on your birthday. Obviously, it's all a bunch of bullshit, right? But people love this stuff. They can't get enough. Okay, I hope I've made my point. Remember, Kate and friends, it's called the precession of Earth's axis tilt, chosen by the star child. Can we rename you here? Okay, so okay, right. So yeah, all right, star child. Okay, there we go. All right. Anyways, so sometimes they call it the precession of the equinoxes. They sometimes call it the 26,000 year precession of Earth's axis tilt. It's real. It's important. Okay, I say we've completed our lab for the day. So here's what I'd like to do. The sheets that you will turn into me are this sheet and this sheet. Don't worry if you didn't get to do your zodiac sign. There was a lot of participants in this video right now. There's a total of, oh my gosh, it looks like 20 or 30 of you. So we would be here all day if I did it for everyone. Now that I've done that, I want to hide you guys again. Wait, how do you do that? In the video settings, I can hide non-video participants. Okay. So you're going to turn in this sheet and you're going to turn in this sheet. Question for the class. Can I entrust you guys to upload this? And make it look good? Okay. You guys already have some experience, so that shouldn't be too hard, right? Devlin Starchild, because you are the chosen one, it's imperative that you get all of your labs and homeworks into me right away so I don't have to give you any mystical zeros, okay?
Alrighty, I just have one question. If I was to be rewriting these, like copying down the worksheets, would I be able to remake the tables in Word and send you a document, or would you want me to take a picture of it?
I'm cool with either one, Devlin, but what I would say is, since you've got a backlog of work to do for me, maybe you should just snap a picture of whatever you wrote down and be done with it, and then call up those YouTube videos and fast forward to where we do the homework in lab. The labs only take an hour, so you can crank out lab 1 really fast. But homework 1, if you remember, the homeworks do take a good solid almost 2 hours. And oh my gosh, did you see? How did you see that sandwich? Can I tell you about?
I was thinking that all class too. I was like, that's a
wait. You guys could see the sandwich in the corner. My father lives in Smithfield, and he has this amazing garden. It's so huge, and he grows all these garden fresh tomatoes and cucumbers, and he's got squash and berries. And so he made this. He gave me like a huge basket of vegetables, and I made the most amazing tomato sandwich. It had mayo, pepper, salt, and it had Hungarian wax peppers on it. I'm a little bit of a pepper enthusiast. And it was so, you know what, Austin, I used to think mayo was gross too, but my father taught me that mayo works so perfect in one case, and that's when you make a garden fresh tomato sandwich. The combination of pepper, mayo, and tomato is like a holy experience. I was so inspired that I did take a picture and I sent it to my friends, and thank God that's the only picture you guys saw. Okay. So that's always the fear, is when I'm on my cell phone, something embarrassing is gonna happen, which I'm sure will happen before this class ends. So anyways, so why don't you guys turn it in, okay? I've got a tomato sandwich to eat. And do you guys want to ask me any questions before we stop here, or is everything pretty self-explanatory? Okay. So Devlin, get that uploaded right now, and I'm going to keep it open until maybe tonight at midnight, or maybe I'll do it tomorrow morning. That'll give you some time to get those 2 in, okay? And by the way, that goes, anyone who isn't Star Child, if you didn't turn in your homework 1 and lab 1, I'm going to give you this little grace period to get that in. But going forward, oh, is that a ferret, Emily?
That's a furry boy.
What's the name of that little guy? You're muted.
I have 2. That's Honey, and they're running around my room right now. Come here. And this is Tubby.
Whoa! Oh my gosh, they're amazing. They're amazing. That's so fun. Yeah, they are so cute. We got to get
so
them
energetic right now.
We have to get them to meet Buff the raccoon. Although I don't know if Buff would try to eat them or what, but Buff is a little savage. Anyways, Emily, those are killer pets. I love oh yeah, Donovan, seeing your dogs, the parakeets, the pets are so great. Can I tell you that last semester, one guy in my class, he had a rooster, and he would just sit there for the whole class with the rooster in his lap. It was so outrageous. These are one of the hidden perks of doing online classes, so we have to enjoy what we can.
Was that Nate?
Yeah, you know Nate.
Yeah, I'm actually good friends with him.
Oh, it's great. Yeah, he's a cool dude, and he's got, I think it was a chicken or a rooster, but it's great because the video, like they always choose a thumbnail for YouTube, and the thumbnail they chose was of him holding his chicken. So anyone who had to watch that was like, what the hell? Okay, guys, I had fun hanging out with you as I always do. Okay, well, Kaitlyn, we want to see your cat at some point, so you better give her some of that catnip or something, narcotize her. Guys, turn in your work, turn in your labs, and I'm going to see you Thursday morning at 11:30, right? Have your calculators, be ready to do some homework. Peace be with you, all right?
Thank you.
Bye.
Have a great day.